Great. So our next speaker today, we're happy to have Irene Seifert from Heidelberg University to tell us about periodic delay orbits and the Polyfold implicit function theorem.
Yeah, thank you very much for the invitation. And maybe I should say in the very beginning, to not forget it, that all this is joint work with my supervisor, Peter Albers. What I want to talk today under this title of periodic delay orbits in the Polyfold implicit function theorem is an existence result for a family of periodic delay orbits. And this at the same time gives the first examples for the use of polyfold theory in this whole field of differential delay equations. And we think that there are good reasons to maybe use it for other problems as well. So the plan for today is first explain the setting a little bit and give the main result. Then I'll talk about the strategy of proof and give a very short reminder on polyfold theory. Then I want to say some words about the proof, and if there's time, I'd like to talk a little bit about possible generalizations of our result. So we start in the setting in R to the n, and we consider a vector field, time-dependent smooth vector field on Rn, and then we take a parameter tau in the reals, which we call the delay, and consider this equation, namely x dot of t equals the vector field at time t, but evaluated at the point x of t minus tau. And for this equation, we are looking for one-periodic solutions. When we see this equation, there are some things we may remark in the very beginning. One is that, of course, as I wrote it down, this equation only makes sense in Rn because the left-hand side lives in the tangent space at x of t, and the right-hand side lives in the tangent space at the point x of t minus tau. And on a general manifold, we have no way to canonically identify these. But of course, on the manifold, we can consider other more complicated equations which also involve this time delay. Second thing is, this is really non-local. So x dot of t does not depend only on something and x of t, but really on something which we'd call the past of the trajectory x. This makes everything a lot more complicated than for ordinary differential equations. For example, the solutions of such an equation do not form a flow on Rn, because we cannot just start at a point and go where the vector field leads us. We have to know something about the history before, so this gives a semi-flow on a function space. And third thing I want to mention is that this equation is not smooth in tau, but I'll talk about this later. And then, of course, you see for tau equal to 0, we just recover usual orbits of the vector field x. So the idea is now to vary this delay, tau near 0, and study the one-periodic solutions, whether they persist or not. This is now our result. We assume that we have a non-degenerate one-periodic orbit of the vector field x. And then we show that for every small enough delay near 0, there exists a locally unique solution of this delay equation, so a one-periodic. And also that the parametrization by delay is smooth. Maybe this, well, I think it's not very surprising, this existence result, but still I think it can be found nowhere. And also the smoothness of the parametrization is kind of astonishing, because all the smoothness issues in the delay equations literature, you never get something which is better than C1. Although, of course, in this setting, you might expect it to be better, but it seems difficult to prove. And we can then generalize this also to finitely many discrete delays, or to suitable delay equations on manifolds, or hopefully also to certain cases of time-dependent delay. We'll come to that in the end of this time. So, of course, the solutions that we're looking for are the zeros of this map, which takes a delay and a loop and maps it to the difference of x dot and the vector field evaluated at the shift loop. And if we start with an orbit of the vector field, then we are given a 0, namely the pair 0, x0. And so we want to claim that the 0 set of this section, this map, near this pair carries the structure of a one-dimensional smooth manifold, and also that it is not contained in 0 times the C infinity loops, because then we wouldn't get solutions for different delays. So of course, the thing we want to do is that we want to use an implicit function theorem. But now comes the problem that this shift map taking a delay and a loop and mapping it to the shifted loop is not a smooth map. But at the same time, that's why we use the scale calculus and the polyfold implicit function theorem, because it comes very naturally. First, let me maybe talk a little bit how far we can get with a classical differentiability setting. So for shortness, by HM, we denote the loops in Rn of Sobolev class M2. So in particular, H0 is the L2 loops. This gives such a sequence of compact and dense embeddings of these spaces into each other. And now for a given delay and a loop, we define the shift of x by tau, well, just to be what we want it to be. And from this, we directly see that if the loop we start with is of class Hn, then also the shifted one has the same regularity, of course, and in particular also the same norm. And now some facts about the shift if we see it as a map. So if we see it as a map from the reals to the linear operators from H0 to itself, then it is not even continuous. But if in fact we see it as a map from the reals times H1 to H0, then it is continuously differentiable. And the derivative is what we just would compute by chain rule or whatsoever. So, well, now we can write this map S, which cuts out our solution space using this map phi. And then we directly see that this map S is continuously differentiable, but it is not smooth on any fixed level R times Hn. So we can use a C1 version of the implicit function theorem for Banach spaces, and this gives us a C1 manifold of smooth solutions. So in particular, the existence of these solutions is done in this way. But this can only provide a C1 parametrization by delay, not a smooth one. And we might try to fix this by starting with R times H2. Then, of course, we really gain another derivative for this map S, but then we directly lose the Freighton property, so no chance of applying an implicit function theorem anymore. But those of you who know scale calculus directly see that, well, this is what we need here, and it comes naturally and solves the problem. So a very, very short reminder on polyfold theory. It was developed by Hofer, Wysotsky, and Zehnder, and it is used for the study of moduli spaces of J-holomorphic curves. And in this setting, like, there are certain problems that always occur, and polyfold theory was made to deal with these problems, namely the one of varying domains, varying automorphism groups, transversality issues, and which is the one which is important for the delay setting, the non-smoothness of these parametrization maps. And of course, all the details can be found in the big book, Polyfold and Freighton Theory, which you can find on the archive. The main ingredients here are the scale Banach spaces to start with. So a Banach space with a filtration by subspaces, which are Banach spaces on their own, with compact and dense embeddings. And then a notion of scale differentiability for maps between these spaces. This is what is called scale calculus. And then to mention the words polyfold, at least sometimes in this talk, the n-polyfolds are topological spaces that locally look like not only open subsets in the scale bundle spaces, but like open subsets of scale retracts with scale smooth transition maps. And the polyfolds then additionally also allow for orbifold behavior. And well, some very important results. The first one is the chain rule for scale differentiability, which is really not obvious from the definition because so it really is a theorem. And then an implicit function theorem for scale smooth scale Fredholm sections. And here the scale Fredholm property is more complicated than just giving a splitting of domain and target, but it really needs some extra conditions, otherwise the implicit function theorem couldn't hold. So this implicit function theorem, what does it say? When we start with a tame strong n-polyfold bundle, which admits scale smooth bump functions, and we have a scale smooth section, which additionally has the scale Fredholm property, and it is what is called in good position. Then the zero set of this section is a smooth manifold, so really classically smooth manifold of dimension equal to the Fredholm index. So now, what do these objects look like in our setting? The scale spaces which we have are the ones which we have already seen in the classical setting. So one is the space of two loops with the filtration of loops by higher regularity. One here is the shifted, more or less the same scale space, but shifted by one. So we start with a W1, 2 loops and then have the same filtration. And R with its constant scale structure. So all the spaces in the filtration are R, and the inclusion is indeed compact and dense. From this, we can form a trivial bundle. Here, R times H1 times H over R times H1. Here, the triangle is as a set, just the Cartesian product, but it means what is called a strong bundle that we considered with a certain double filtration. And then the map, which we've seen quite a lot now, becomes a section in this trivial bundle. So here's again the implicit function theorem. We have this trivial scale Hilbert space bundle. We have the section. For the Fredholm property, we need to work. And the meaning of good position in this very easy setting really means just that we need to get transversality in the given solution. And indeed, with Peter Albers, we could prove the following, namely that this section is really a scale Fredholm section of index 1, as we want it to be, and that if the orbit with start with is non-degenerate, then the linearization is surjective. So about how to prove this, the scale smoothness of S is of course immediate as soon as we know the scale smoothness of the shift map. And this was shown in a paper by Frauenfelder and Weber. So what we had to do was to check that it really satisfies the scale Fredholm property. And for this, we used the criteria given by Kathleen Verholm. And for the second one, more precisely, we showed an if and only if statement, namely that this restricted differential only going from H1 to H0 is surjective really if and only if the orbit is non-degenerate. And this then also directly implies that the one-dimensional local solution set, which we are interested in, really projects to an interval around 0. So this, together with the Polyfold implicit function theorem, implies the main theorem. Not only the existence, which we could get by classical means, but also the smoothness of the parametrization. Okay, I think I'm going very fast, so I have a lot of time for the generalizations. The first one was to finitely many discrete delays. And by this, I mean equations of this form, where we have a map, which is now not a vector field anymore, but just a map taking a time and k vectors in Rn and giving another vector. And we take k discrete delays, so k numbers in the reals, and evaluate the trajectory at these k different points in time. And then by diagonal embeddings, the function x then defines again a vector field on Rn, and we need to start with a non-degenerate orbit of this vector field. And in this way, immediately we get a k-dimensional solution manifold. So for all small k tuples of delays, we have a solution, and then also smooth parametrization by these tuples. The second generalization I wanted to mention was on manifolds. And for example, we considered this equation where inside the vector field, we do not consider any delay, but we have a function in front of the vector field, and this one is delayed. And in this setting, of course, instead of linear scale Hilbert spaces, we get a scale Hilbert manifold and then also a non-trivial bundle, but still without any complicated things like the retractions or boundaries or corners. And in this setting, we need to assume something more about the orbit we start with, because otherwise the non-degeneracy of x0 maybe does not imply surjectivity. So we assume that this pullback bundle is trivial, but then we get exactly a one-dimensional solution manifold exactly as before. And the third generalization is the cases of time-dependent delay in Rn. This is the most interesting one, but also still work in progress. So by this, I mean equations which look more or less like in the beginning, but now the tau is not just a real parameter, but it is a delay function. So let us say a smooth function. Well, then to have any chance of a Fredholm operator, of course, we should vary this delay function only in a finite dimensional subspace of C infinity. But then also, even in this setting, it is, well, it's possible to write down examples where this just doesn't make sense and where you cannot get such a solution manifold. So one needs some more conditions on tau. So yeah, what we plan to do is to show that if we have the right conditions, then all the rest goes through exactly as we would like it. Okay, so what I have done today is we used the scale calculus and the Polyfold implicit function theorem to prove the existence and local uniqueness of these one-periodic orbits. And the most important thing, because it's the stuff that cannot be done in the classical setting, that the parametrization is smooth. And well, we hope that polyfold theory may be of help also for other questions inside this field of differential delay equations. Okay, I think I'm already done with it. So thanks very much for your attendance.
Thank you. Questions?
So, Irene, is it possible that one could define some kind, for example, in R to N? So I look at a symplectic domain and I take a Hamiltonian form of the delay equation, So, and to define some kind of a capacity, is it feasible that if I put so when you look at the so-called Hofer-Zehnder capacity, you take very particular Hamiltonians and measure how high you can go without creating short periodic orbits. So I wonder if one could study delay equations there as well. If one could think of a phenomenon, if the energy is too high compared with the delay and so on, then you will get short periodic orbits. If that would be true, then maybe by playing around with this thing, one could get additional invariance. So I wonder if there's even any hope for this.
Okay, that's well, a very interesting question. We have not thought about this. So when you say Hamiltonian delay equation, so do you, in what sense do you?
Let's take it in R to N, so then we don't have too much problems. Yeah. So you just take the Hamiltonian vector field, put the delay in there, like what you had, and say, now I'm studying one periodic orbits. Now, if the question is if the energy variation, so suppose it's flat somewhere and goes up, if it goes up fast enough, I get a one or even shorter periodic orbit, I wonder. One could expect something like this. If you could, then you could define a delay capacity. And that might be a new invariant. And then you had the other construction with different delays. So maybe one can mix something up and playing around with the delay. And the delay would, you see, because you look at the history, you would check out different parts of the space and get some invariance. So maybe playing with different delay parameters, you might then get some kind of a profile, a better profile of the space you're actually looking at. I don't know. I mean, just some fantasy. Yeah, so.
Yes. Sounds like an interesting topic to think about. I mean, one problem is still that here we could show transversality at the orbit, but of course, as soon as we really work with a delayed orbit, then it is not at all clear what the transversality should mean geometrically, at least not to me. So this might be a little complicated, but definitely something to think about.
But I guess that is what you are paid for. Yeah. Some complicated problems.
Definitely.
So for the closed orbits, I'm not sure one can hear me because my thing is broken.
I can hear you.
We can't see you, but we can hear you.
Yeah, that's good this way. Everything is broken here. When you take, for instance, the Hamiltonian 1/2 in the plane, Z norm square, and you take tau small, then you get spirals that scroll in. So there is, for instance, no volume preservation, and everything goes to the origin, and only the origin is the fixed point stays. So there is nothing like a foliation, at least for some very easy systems one can compute. So I think one really has to be very careful. Maybe there is still a profile because this works only for certain taus. But so the existence theory for closed orbits is for these already in simple examples very different. But I mean, it doesn't mean that.
You thought about this, so you have some global results?
No, I just say that examples.
No, I say what you said, but did some people study global results for these equations?
Urs, do you remember? So the existence theory is kind of lousy for the Hamiltonian delay equations. When you take I gradient H, even in R2n, only for extremely special Hamiltonians. Essentially nothing is known, right, Urs? Oh, now Urs is in.
Yeah, right. Here you don't have variational approach.
Yeah.
If you do just time shift.
Mhm.
So there is no minimax and no linking.
Yeah, so the problem is, of course, when the difference, the Hamiltonian part, you get also the delay for the variation, and I guess that's causes the problem.
So if you do variation approach, you often get something like delay and prolay.
Yeah, but maybe that's not bad. I mean,
Right. Yes. Yeah.
I mean, but in some sense, you see, the idea about understanding a symplectic space is to explore it. And one way to explore it is to put all kinds of Hamiltonian systems on there and see what one can measure. And maybe at some point when you work harder, and you have an abstract definition of what a space mission is, yeah, we have space missions with fuel, and we can fly through the symplectic manifold and explore it. Yeah? So, and why not something with delay and pro-delay? I mean, a variation of this. Urs, are you frozen or stunned?
No.
Excuse me, I have a question here. So, if you consider, so usually there are many unstable periodic solutions in systems, for example, like circular three-body problem or van der Pol equation. So, which means that if you slightly perturb those solutions, then they are not periodic anymore. So I would imagine that this slight delay in your equation, well, it's somewhat analogous to perturbation. So I would imagine that delaying it a little bit would actually have some interplay with this instability issue. How would you comment on that, please?
So I have to admit that my intuition concerning these delay equations is maybe not very good. So at first I'd say rather not, because they seem to be very strange, but of course that's not a good argument. It could still be that you can get something like that.
Well, let me try to ask differently. So, does your proof involve some kind of stability argument?
Well, depending on what exactly you mean by stability argument, I mean, the non-degeneracy condition is something which I'd say is some kind of stability.
Can I actually ask to that point, if you start
maybe with... I didn't get your point.
If you start with a solution, I mean, maybe this is a different question.
We do need to start wrapping up though. So maybe if there's time later, then we can, or unless it's a very short question, because we have 1 minute.
Oh. Well, I just wanted to ask, if you start with a solution for a given delay, do you also have existence for nearby delays? Or is it just if you start with a solution for no delay, for the possibility?
So the problem with the solution with delay is just that we have no idea how to say something about transversality. As soon as you have the transversality, then of course you have exactly the same thing near this delay. But saying whether or not such a solution is transverse means solving another delay equation. And well, yeah, that's what we couldn't interpret geometrically.
And on that note, let's thank the speaker again.